Uh, Good evening, students. Uh, in this video, we will try to overview what all we have covered in the week one. We started with unit one, sustainable chemistry and e-waste management. Now, this particular unit is classified into three different aspects. To begin, we focused on biomaterials, that is, the materials that are of biological importance. Uh, the in this particular section, we focus on the aspects of biodegradable and biocompatible polymeric materials. Uh, what is to be important to be noticed in this case is we are going to study on the polymeric materials which are in contradiction to your metals or alloys, superconductors, and any nanomaterials. As a matter of chemistry, we'll focus on synthesis and applications. Next, we move to the principle of green chemistries. We have 12 principles. Now, remember that all the principles of green chemistry is focused on to carry out any reaction using less toxic chemicals and low reaction times. By and large, everything is focused on these two aspects without compromising on the efficiency of the reaction. We do not want to just because by using less toxic chemicals, it is not that the product yield is affected drastically. We are choosing such chemicals such that the product yields still remains at the significant level uh, by reducing the toxicity generated by the overall reaction. And at the same time, we want to reduce the kinetics, we want to increase the kinetics of the reaction by carrying out the desired reaction in a very low, at low times. Instead of say 12 hours, we want to modify the reaction conditions and we want to get the same yield in 1 hour. So all these 12 principles are broadly based on these two aspects. Of course, the last one is the cost effective approach. We want to reduce the financial investment on all these commercial reactions. For example, in the drug in the manufacturing of a drug or any drug. Okay, if a current protocol is utilizing 1 lakh to get 100 grams, so we have to focus in a way that is it possible to reduce the amount uh, by and without compromising on the quantity and without compromising on the quantity of the yield. Likewise, the e-waste, whatever is referred here, okay, it's electronic waste. Okay, any electronic circuits, if you consider, to have a valuable metals. It can be copper, silver, gold, lead, something like that. Okay, so how exactly we are trying to manage in the sense how we are going to recover these materials through various metallurgical process, hydrometallurgy, pyrometallurgy, and direct recycling. Extraction of valuable from the e-waste. Battery waste management in the sense, if you are very particular to focus on nickel, cadmium, or lead in the lead acid batteries, those is referred to as battery waste management. Finally, we are focusing on circular economy case studies. Is it really benefiting our society in that sense? Or what is the cost involved and what is the current progress in this particular area? So, these diversified aspects will be dealt in Unit 1, uh, Sustainable Chemistry and E-Waste Management. Uh, to recall from your the basic definition of polymers, now we have two major methods to obtain the polymers: addition polymerization and condensation polymerization. Okay, in the case of condensation polymerization, there is elimination of a small molecules between the two monomers. In the case of additional polymerization, you do not have such instance. It's mere an addition of two different monomers. Based on the molecular forces, polymers are again classified into thermosetting and the thermoplastic. That is, once you heat and allow it to cool, if it is retaining its hard, if the polymer obtained is hard, you call it as thermosetting. If it is in the melt state, you regard as a thermoplastic polymers. Depending on the nature of the carbon chain backbone, uh, another classification recently emerged, whether it is degradable and non-degradable. But we do not have any instance to claim that these particular polymers are non-degradable, given the emerging of many technological process. Okay, we can only say it is difficult to degrade. So if you have a polar functional groups, those polymers are susceptible for rapid degradation. If it is non-polar, it's difficult to degrade. It doesn't mean that it cannot be degraded. Under using some harsh conditions, it is really possible to degrade any polymers. What exactly we mean by a polar functional group in the sense, see, if you have a carbon uh, polymer, where you have a carbon principal carbon chain, and the terminal carbon, if it has, say, polar functional group. Polar functional group refers where there is a separation of charge. Oxygen being more electronegative, it takes a delta partial negative charge. As a result, carbon forms partial positive charge. Anything that is with a negative charge, you call it as nucleophilic center, nucleophile or nucleophilic center. This positively charged carbon center becomes the electrophilic center. Now, as a result, what happens in an assumption that if you add any an attacking molecule, if it has OH minus as a nucleophile, it will definitely attack carbon. And in the case, if you have H plus as an electrophile, it will definitely attack O minus. As a result, what happens? The terminal carbon tends to undergo cleavage. Similarly, assume that you have an polymer with the chlorine side chain functional groups. Again, delta minus and delta plus. So the carbon can undergo cleavage at this point. So your polymer breaks down into oligomers, and in subsequent reactions, finally you get back your monomer. So that is the advantage of having a polar functional group. You have a suppression of charge, add a nucleophile or an electrophile, it rapidly attacks the sites and results in cleavage. But if you have a non-polar group, okay, just like methane, okay, very difficult cleavage under the ambient conditions, under the moderate conditions. Okay, so that's the advantage in this case. Before understanding the biodegradation, which is the crux of our the syllabus, we'll understand what are the different types of degradation that is currently in process. To begin with, the thermal degradation. Take polymer, just heat it at higher temperature. Any molecule undergoes a subsequent oxidation. By and large, you get the carbon monoxide or carbon dioxide. If at all, if the uh, any nitrogen functional groups are there, you end with ammonia gas or even sometimes amines. The catalytic degradation, it is almost similar, except that you carry the reaction in the presence of a catalyst particles that can increase the rate of the reaction. So here the catalyst increases the rate of the degradation. Hydrolytic degradation normally refers where you use water. Remember, water has H plus and OH minus. Okay, so it behaves as an electrophile. OH minus behaves like a nucleophile. If you have any polar functional groups, these two agents simultaneously attacks and degrade the polymer. In the case of photooxidative degradation, normally the principal carbon chain results in the formation of a radical. That means whatever the covalent bond that you see is made up of two electrons. Okay, it's made up of two electrons. So under the influence of high intense light, okay, the polymer chain breaks. As a result, you get carbon radical. In the presence of oxygen, there is a high tendency that it forms peroxo radical. Later, the cleavage takes place at this site, forming alkyl radical and carbon dioxide molecule. Okay, carboxylic acid are also formed, provided you have OH as the functional groups. So mechanical degradation. In this case, you can clearly observe that you have the reduced molecular weight. That means high molecular weight polymers transform to low molecular weight polymers. It will not result in complete degradation. So as a result, what happens to achieve complete degradation, whatever the reduced molecular weight you got here, either it should be subjected to photooxidative, thermal, or catalytic, or even hydrolytic. Okay, so the uh, compared to these four processes, mechanical degradation doesn't result in complete degradation. You can clearly state. Finally, what we have is the biodegradation. See, thermodegradation is the prefix you understand, and under the influence of heat. Photooxidative degradation under the influence of light. Mechanical under the influence of some stress. Milling. Hydrolytic under the influence of water. So the here biodegradation, okay, it only indicates in the presence of biological species. Okay, the major advantage of this process is you can easily carry out at room temperature and no harsh conditions. There is no harsh condition. In a big reactor, take polymer and just pour your bacteria and close it. The degradation proceeds, even though slowly, it proceeds on its own without producing any harmful gases. Okay, that's the advantage. As I said in the just to glance, mechanical milling, the polyurethane, when you just place it in between the two mills, okay, these are all metal balls. Normally, alloys are also used. So when two metal balls hits, okay, the polymer, what happens? It crushes into powder. And it finally ends in the your low molecular weight polymers. This is the situation with photo degradation, photo oxidative degradation. Okay, though a complicated one. As I said, you have initial reactant R dot. I'll just write it here. You have R dot, and there is a you can see at the top. Okay, you have oxygen. So finally, you are getting RO dot. Now to this ROO dot, if you add alkane RH, what is R dot? Okay, this ROOH dot is unstable. It forms RO dot. OH dot will be there. It can react with H dot forming water. You have H dot, then what happens? It forms water. This RH, as I said here, you get water. This RO dot, it can also react with H dot forming alcohol. Okay, some cleavage can happen even at this particular site. You can end with RH. Okay, so these are the speculative steps that are proposed once you get the products. So initial reactant is alkane, okay, RR, alkyl and alkyl group, alkane. Finally, you are ending with alcohols. Okay, what are the byproducts that you're observing? Water. It's not a harmless substance. That's how these photooxidative degradation took, precedence in recent years. A very convenient method to obtain alkanes to alcohol. As I said, degradation means I understand that there is a change in the chemical composition. Alkane you have, alcohols you got. Okay. No, just like you have a nucleophilic attack and the electrophilic attack, enzymes are very much particular. That means if you consider oxaloacetate as an enzyme, it only attacks carbon-carbon single bond. Esterase attacks carbon-oxygen bond. Asparginase attacks carbon-nitrogen bond. Phosphoamidase attacks phosphorus-nitrogen bonds. So, for example, if you have any nitropolymers, uh, you have to add both oxaloacetate and asparginase for complete degradation. If you have only polyethylene chloride, polyethylene, for example, CH2, polyethylene chloride, your addition of oxaloacetate can result in complete degradation. Okay. In the end, if you have nitroethylene, then what happens? You have to add even asparginase. Likewise, various enzymes are there to cleave particular bonds. So this is you can consider as a drawback with this biodegradation. Because when you consider a polymer with the multifunctional groups, then you have to add more enzymes, and there may be a mutual interferences between the enzymes to attack the particular bonds. As a result, the expected kinetics tends to get inhibited or gets slower. So in this mechanism of degradation, the basic steps that there is microorganisms, first it secretes some enzymes. These enzymes, you can see you have a polymer, the enzymes, what happens over this polymer surface, uh, these enzymes goes and it forms a certain sort of a complex like a structure, not exactly complex, it's a simple adsorption. Okay, previously there are a literature which proposes it forms an enzyme polymer complex. Literatures are do there, but uh, by and large, we only consider as an adsorption. It's a physical adsorption. Chemical, not to that extent. Okay, and it is always a monolayer. Okay, when enzymes gets adsorbed on the polymer, remember polymer serves as a food for enzymes. Actually, that is in the practical sense. Actually, that is the reality. Okay, these enzymes eats your polymer. So what happens? Okay, the residual polymer, okay, just breaks down. Depolymerases, that means any enzymes, it can if it can convert your polymer to oligomer, dimer, and monomer, you call it as depolymerase, a fragmentation of your carbon chain, depolymerase. Okay, so initially you get oligomer, then dimer, then the monomer. So the first step is the secretion of enzymes by the microorganisms. Second step is your physical absorption. Next is your cleavage of your covalent polymer chains or covalent bonds. Then you observe the end products. So in these enzymes, in this biodegradation, you have two different kinds. One is aerobic condition, other one is anaerobic condition. Aerobic condition refers to presence of oxygen. Anaerobic refers to absence of oxygen. Uh, in the absence of oxygen, what happens? Methane forms as a major product. In the aerobic conditions, methane doesn't form because whatever the methane that is formed, it in the aerobic condition, it reacts with oxygen, forming carbon dioxide and water. That's the mechanism of the degradation. Now, what are the requirements for a degradation in the sense? First is rate of degradation should be greater than rate of accumulation. Okay, understand. Rate of degradation should be greater than rate of accumulation. That means when polymer degrades, you get the products obtained in sequence, oligomer, dimer, and monomer. The rate of accumulation there, it actually refers to the accumulation of oligomer. It's not that monomer concentration obtained is very less compared to the oligomer. Let us understand in the logistic way. Assume that you have 10, 10 moles of oligomer. 10 moles of oligomer. It may take, say, 1 hour for every 10 moles of oligomer to transform into 1 mole of monomer. Okay. Here, the depolymerase. Okay. Uh, let us understand. Okay. For every 1 hour, your polymer is breaking into 10 moles of oligomers. Okay. Here to here it is very fast. Here it becomes slow. So when it comes to the second hour, okay, what happens? This 10 mole may be reduced to 9 moles, but additionally 10 moles oligomer is excessively formed because of the cleavage of the polymer molecule. So what happens? The accumulation of these byproducts will be more compared to the formation of the monomer itself. Okay, so we have to alter the reaction conditions that uh, the rate of degradation, that is, even the oligomer should completely degrade to monomer in the order of less than on the minute scale. Okay, at least if it is taking 1 hour here, even less than in the half an hour, all the 10 moles of oligomer should be transferred to monomers. Likewise, we have to uh, monitor, alter. Otherwise, the byproducts will be more in concentration rather than the desired product. Intermediates should be less toxic. That means whatever the oligomer that we obtain, additional byproduct during this course, it should be less toxic in nature. If it is more toxic, what happens? Extraction of these useful products becomes a major difficult issues. End products always should be commercially useful, either mineral acids or the biomass. Duration, when you consider the duration of this degradation, it must be very short. See, short in the biodegradation, it's not in the nanosecond scale or the millisecond scale. Normally, we consider for week or months only for an effective biodegradation, not years. You should not take 1 year to degrade 1 gram of polymer. No, it should be around the week. That would be sufficient. Factors, what factors can influence is humidity and the temperature, of course. Um, since we always focus on to carry out any degradation at room temperature uh, from cost-effective process, okay, we have to monitor all the degradation reaction at this particular temperature only. Humidity you can easily control. Um, Humidity, nothing happens, but uh, sometimes there are issues that uh, when the excess water molecules are there, enzymes becomes inactive. Okay, that's the only reason. The concentration of your enzyme becomes diluted. Uh, Molar masses, what are the factors associated with the polymers is in general understand that extent of cross-linking, if it is too high, okay, degradation becomes difficult because see, assume that you have a simple chain, linear chain. Easily, enzymes can cleave this molecule, principal chain. If the principal chain is having uh, more alkyl groups or aromatic rings, okay, side chains, okay, the time taken to degrade this aliphatic carbon chain is different from for the degradation of aromatic rings. Okay, the side chain will be very less reactive always when it comes to biodegradation. So uh, more times is more time is required for complete degradation. As I said, molar mass in this case, molar mass in this case refers to the high molecular weight. Always low molecular weight is more preferable for degradation with enzymes rather than high molecular weight. Crystallinity is just arrangement. Crystallinity and extent of cross-linking are one and the same. Defines the structural configuration of your polymer chain and also the substituent. Uh, Here, if you consider, see, you have assume that you have this type of polymer chain. Okay, if all the groups have only X substituent, then crystallinity is very good. But if you have X here, okay, and one more substituent Z, another substituent Y, then crystallinity is random because above the plane of the molecule you have different substituents. Below the plane of molecules you have a different substituents. So the order of arrangement of atoms will be random. So crystallinity is reduced. So even in such case, your degradation will be ineffective. As I said, for each bond, you have to add different enzymes. One enzyme may degrade carbon-carbon bond very fastly, but other enzyme may take less time to degrade carbon Z bonds. Okay, likewise, XYZ refers to substituents. Take any substituents of your choice. Okay, porosity, last we do not have any conclusive study to state that more porosity means more the degradation. But commonly accepted definition is if the polymers are more porous, uh, the solvent molecules can easily enter into these pores. Um, for example, water, if it can initiate hydrolytic degradations. Okay, so even if it is a more porous, you can easily rupture because of you have too many cavities within the polymer structure. Okay, so that's about the factors affecting degradation. Just to sum up, uh, understand uh, you have the polymers. We are focusing on biodegradable polymers. Okay, in general, degradation would be easier if you have polar functional group compared to the non-polar functional groups. Only because if the bonds are polarized, then it is susceptible for electrophilic and nucleophilic attack. Several types of degradations are there depending on the conditions that is adopted. If you are adopting heat, you call it as thermal degradation. Same thermal degradation, if you are carrying out with the in the presence of a catalyst, you call it as catalyst degradation. If it is in the presence of a light, you call it as photooxidative degradation. And if it is in the presence of a ball milling, you refer to as mechanical degradation. In the presence of water, hydrolytic degradation. In the presence of enzymes, biodegradation. In this at this stage, understand that in the mechanical degradation, it only transforms high molecular weight to the low molecular weight polymers. Photooxidative degradation, you have the participation of free radicals. Thermal, under the very harsh conditions are used and complete degradations are achieved. Uh, and the catalyst, it only increases the rate of thermal degradation. Hydrolytic, in the presence of water, again, it's merely an electrophilic and a nucleophilic attack. Biodegradation, as I said, it's in the presence of enzymes. Just to increase our understanding, just consider a polyurethane foam, a polymer. If it is placed in between the two ball millers, okay, that will be operating at very high speed. It crushes your polymers into pieces. That is powder. Here, as I said, degradation, you should not yeah, be under the assumption that it is something leading to the destruction. But in chemistry, it is always it's a transformation from chemical. There is a change in the chemical composition between the reactants and the products. Here, the best way to obtain alcohol from alkane is passing through several intermediates. Okay, as I said, you can have R over bond. The dot, whatever I have represented here, is a free radical centers. Water is always a byproduct that is that is not considered as a toxic. So relatively, your photooxidative and the biodegradative are the two more important pathways that are environmentally safe. Um, just like in chemical reactions, you have site-specific attack, likely in biodegradation, as a few enzymes. Only those enzymes attacks particular bonds. Oxaloacetate, if you have carbon-carbon bonds, esterase, carbon-oxygen, and likewise. So it indicates that if you have a polymer with multifunctional groups, you have to use various enzymes, which is in fact a major drawback because we do not have adequate understanding on the mutual interferences of these enzymes in the reactor. Whether oxaloacetate will be still active in the presence of esterase or it may become inactive also. Okay, such situations are very normal. Now, how could we understand the mechanism is an enzyme, microorganisms, when it excretes enzyme, it initially adsorbs over the polymer surface, normally physical adsorption, although complex formation is also reported, but by and large, we consider physical adsorption. Um, Once it adsorbs, polymer serves as a food for the enzymes. In fact, that is a very crude word that is being used in any biological textbooks. Your enzymes eats away your polymer. It breaks down into fragments. Depolymerase, always remember the conversion of polymer to monomer by any enzyme, you call it as depolymerases. So it transforms to oligomer, dimer, and monomer in the course of time. At this stage, remember you have two different types of degradation: aerobic condition and anaerobic condition. In the absence of oxygen, methane will be the major product. In its presence, methane reacts with oxygen, forming carbon dioxide and water. Therefore, you will not observe the formation of methane in aerobic conditions. How well we can make this degradation process more safe for our environment is your intermediate product should be less toxic. That's how you have to choose the nature of the enzymes. And end products definitely it will be mineral acids and the biomass. Duration should be very much operative within weeks or months, not years. Okay, that's how we tune the reaction conditions. Here, rate of degradation should be greater than rate of accumulation. Rate of accumulation in the sense byproducts accumulation. As I said, if you consider that for every 1 hour, a certain portion of polymer is transforming to oligomer. If we assume that it is 10 moles, then it should be completely degraded in the next half an hour so that you have fresh accumulation of oligomers. Otherwise, what happens? If you consider the instance, the 10 moles of among the 10 moles of oligomer, only 1 mole of monomer you are obtaining in 1 hour, then 9 moles of oligomer will be as it is in the next 1 hour. But during that time, your new oligomers also comes. So the rate of accumulation of oligomer will be very high compared to the monomer. Okay, this is a product. This is a byproduct. Okay, that is what it means. Again, um, we are only considering on the reaction to be carried out at room temperature from the cost-effective approach. Um, General trend: increase of temperature certainly increases the rate of reaction, but there are instances where the enzymes may become thermally inactivated. Enzymes may undergo decomposition under the influence of temperature itself. So normally room temperature is preferred. Humidity, understand that if it absorbs more, water, enzymes may become deactive or your overall concentration may be affected, which can alter the reaction rate. As far as the crystalline, when it comes to the properties of polymers, we have crystallinity and extent of cross-linking. Both refers to same. Particular confining to the what you say the the arrangement of side chain substituents over the principal carbon chain. If there is a random arrangement, very difficult to degrade because of low crystallinity. That you call it as extent of cross-linking. That means uh, for a principal carbon in the principal chain, if there are more than one carbon group, that is, if you consider ethyl group, CH3, CH2, okay, two carbon chains are there. So very difficult to degrade. If you have aromatic ring, it is even worse. Okay, so that is the thing. Molar masses, if the molecular weight of the polymer is very high, high molecular weight polymers, very difficult to degrade compared to the low molecular weight polymers. Porosity, porous refers to some a cavity-like structure within the polymers. If it is porous and if it can accommodate water molecules, then your water molecules can enter into those polymers and initiate hydrolytic degradation. Otherwise, not. Okay, but porous is always necessary so that products can be easily evolved. You have to have a space for the exit for the byproducts. But that's what should be your understanding at this stage. Any doubts? Please feel to clarify with me.